peyote is, and again, it would have been too expensive. So thanks to all of you. A couple of things. We're doing Data Day Seattle in October 20th. There will be a graph day. Part of that is a much bigger event. There's 750 people there. Speakers are already coming. Michael, and a bunch of other people said they're going to come. They're a great community. For those of you who live in San Francisco, if you speak at one of our meetups, you get a free ticket to the next Graph Day. If your company hosts one of our meetups, your company gets a free ticket to Graph Day. You know, a friend of Graph Day on all of our meetup, logo on all of our meetup groups. So if you host a bunch of meetups, your whole team's going to go to the next Graph Day for free. And that's it. I've taken up too much of Marko's time. Yes.
Hi, I am Marko Rodriguez. I work for Data Stacks, creators of distributed graph database TSC Graph. I also work on the project Tinkerpop, Apache, creators of the programming language. This talk, you're not going to learn, again, like my last Graph Day talk, you're not going to learn anything from it. But hopefully it's an interesting talk nonetheless. So there's an associated paper with this talk, and this talk is a direct mirror. So hopefully you read it. If not, we'll record this talk. We'll correspond to this talk and the article. So everyone always say, I want to do this talk because I always hear, the world is a graph. Everything's a graph. So okay, let's assume that. Let's take that as an axiom. Everything's a graph. Fine. Of that statement. If we assume that everything is a graph, what does that mean? To think that through, I found 3 problems. Everything is a graph. And so if we're going to understand the world as a graph, then we need to solve these particular, there's definitely others. But these 3 problems have always hit me as represented as graphs. And so this kind of puts the boundaries to what graph databases will do. So first we understand that graphs are everywhere in the world. See that the way energy flows through our country, or this country, through our cities and whatnot, you can easily model as a graph. Structure of this form, vascular systems, the way the veins run through our bodies, jugulars to all the capillaries from the small to the big, power law distributions exist in here, like power law distributions exist in other natural graphs. Exist in these forms. Even to the microcosms, and the very small protein chains. Manufacturers use protein chains. These protein chains can be represented as graphs. Bioinformatics uses this. Representations are very nice. One of my favorites is the galactic filament. This is the largest structure in the universe. Of our planet is in a solar system. Solar systems are galaxies. Galaxies form clusters. Clusters form superclusters, and superclusters form filaments. The spectrum light you see here is a supercluster of clusters of galaxies of solar systems. And it has a very almost neural-looking representation. What we see in the world are very much model a graph. So we go back to this concept of, okay, fine, everything's a graph. And so people tend to agree with this. So what does that mean? Everything. What do we mean by everything? So if we're saying everything, that means the universe, everything that we know, this that we could possibly talk about must be as vertices and edges. And therefore, when we put this back down, we say, fine, everything can be represented as G, E. G being the graph, D being a set of vertices, E vertices. And so then you kind of get this world model where you have all of these different structures we talked about, galactic filaments and DNA and power grids, all just commingling in this one big, massive graph. However, here's the problem. The first problem, and this will kind of start us off. Are evolving the graph? What are the things that are changing the graph? What are the things that are analyzing the graph? Traversals. These traversals, these are the programs, algorithms. To structure the graph, we also have these things that are running on top of the graph. And so in graph computing, we make this distinction. In computer science, we make this distinction. We have data structures and we have algorithms. We classify data structures and algorithms in every computer science course here. And so it's this notion between structure and process. What is the form, and how does that form evolve? Now, the means by which that form evolves become a structure. How does process become form? Graph. And so let's get to the first concept. Process of change. How do we model process as a graph? So this is the definition of the Gremlin traversal machine. So the notation. On the right, G equals VE. Just flip. On the left, we have this psi, which is the function, the traversal function. Enough of a direct acyclic graph of functions connected by streams. Traversors. So one particular traversor is T. Traversors exist in two spots. These traversors exist in the structure, in the graph. They also exist in the traversal. And so traversors move around the graph and they move about any query language, any execution engine, moving down into this. You're going to have pointers into your graph. You can also have pointers into what particular instruction you're executing at the right moment. So they're moving about the graph and they're moving about the traversal. Graph, traversal. Program, processing units. Computer science in a nutshell. Structure, process, processors. And so let's take an example. G equals VE. This is our data structure. This is our graph database. We have some data inside this graph database. Traversal, a little simple one. Knows how to create it. So what you're saying here, Gremlin, is saying vertex 1, and what did they create? What are the creations of the people that vertex 1 knows? So vertex 1's friends, what did they create? Put a little traversor on V1. Knows. So now we say we're at V1 and say he knows 2 people. So then now we have little gremlins on, little traversors on the 2 adjacent nodes relationships to that. For those 2 people, what did they create? Let's assume the person on the left created 2 projects and the person on the right created 1. Therefore, we solved this particular traversal graph. If we want to say that everything is a graph, well, we have to model all of this as a graph. Interestingly enough, that the definition of every gremlin traversal is itself a graph. Functions combined by a set of streams. And so, understanding this, we have a vertex that has a property V and 2 properties. One is its opt V, one is its arms. Has an edge to the next instruction in the instruction set of the program. And the next one is how created. So now we've been able to model not only our data structure, things that we're processing as a graph, or traversal, represented as vertices and edges. Properties. When we get to the first footnote of the article, I'll explain what properties, thinking about how we model properties, strings, and all that. So now we can do our same query. Now we have this little traversor, little gremlin, and we move it about. Now the question is, okay, what about this thing, this program counter, this pointer, this processor, this CPU as a graph? Well, if we go back to the definition, projection, move into G as a projection psi into the traversal. And so we can just model that as a graph. So now we have a new vertex T, and now this vertex projects move or psi into the traversal and move into the graph. Just like we did before, creating vertices and edges as we go. Now we've represented the state of computation as a graph, as well as the data that is being operated on. So psi, our t, and our g, everything is a graph. What we've done is create a static structure, a representation of the executing machine. It's as if we've frozen all the electrons in our processor, and we know where all the electrons are, but they're not moving. A state, it isn't dynamic. These edges. So how do we keep it flowing? Going. How do we go beyond just a moment in time? You can say, well, let's go ahead and create another traversal. Let's call it psi prime. And this traversal is going to traverse this graph that has psi encoded in it. And this is what footnote 2 in the article is. This is a Gremlin traversal that executes a Gremlin traversal represented inside of a graph. So Gremlin is Turing complete, and therefore it can execute itself. That can read a traversal out of a graph, operate on that traversal. Okay. Come on, we don't need to go into the specifics. There's a blog post on it, the Gremlin implementation. Now, psi prime, it's a traversal, so that means we can also represent that as a graph. And in fact, I've encoded it as a graph, and I've taken, using Gephi, I've taken a visualization of it. What a traversal machine looks like. This is the Gremlin machine, the virtual machine encoded as. So, in essence, we have this psi prime. And now we have this t prime, and it's pointing to psi, and it's pointing to g. Everything a graph. We're creating turtle shells, or turtles upon turtles upon turtles. All we're creating is snapshot representations of state, of computational state change. So if we want a great change, we can say, well, I need a psi prime or psi double prime. And this is the problem. If everything is a graph, where does change come from? If everything's vertices and edges, what is time? If everything's vertices and edges, what are dynamics? This chain of computation where every traversal programmed to one and a processor to the other. And what do I mean by this? Computer science, or you look at computers in general, you can say we have bytecode. Now, bytecode is the program of the virtual machine. And the bytecode is processed by the virtual machine. Well, what executes the virtual machine? Well, the physical machine, your Intel processor, that executes the virtual machine. So then to the physical machine, the virtual machine looks like a program. Processor is the physical machine. Well, the physical machine is just a state of computation where all the electrons, memory, how everything's organized. Static state. You still need something to execute the machine. And that's where physics come in. So physics comes in and says, well, I know how to move the electrons about. So physics, we rely on that to alter the state of the physical machine, which alters the state of the virtual machine, which ultimately executes the bytecode. Is who's executing the physics. Where does the chain end? And so we can get to the same kind of metaphor with graphs. I can keep encoding processes, virtual machines, traversals, keep going, stacks into the graph. Know where change comes from. And so if everything's vertices and edges, we fold process and all the process into structure and dynamics. So the first open question, as opposed to the problem in the paper, this graph of everything that we galactic filament to the protein chains to the polymerase to the human vascular system, without requiring something outside of itself. It can just be self-contained. This gets into things like Odell's theorem and Newton's theorem and problem, and there's a lot of nice computer science. And runs into this problem as well. So footnote 1, I said don't worry about strings and properties. So there's a bunch of different types of graphs out there. We know about property graphs, we know about RDF graphs. Typically the graphs that everyone works with have relationships, types of relationships, I knows J. And so I want to show you that without loss of generality, this dots and lines. We don't worry that now we have strings. We have vertices, edges, and strings, and this kind of stuff. No, all you have is dots and lines. Say I knows J. All the different types of relationships that exist in the universe. Then let's say I have a binary. I can make binary encoding. Let's say we only need 3 bits. Nose is represented by the bits sequence 110. The bits onto my edge as opposed to strings. If I represent bits as vertices and edges, here's a simple little schema. B1, B2, bit 1, bit 2, bit 3. And if the bit has a self loop, it's a 1. If it doesn't have a self loop, it's a 0. So now I've gone from a directed labeled graph to a directed graph. And it's a bijection. It's very simple to go back to that node representation. And then you can say, well, you have these arrows. What are these arrows? You have directionality, a type, a way in which things are related. There's you can go from the edges are not just pure adjacencies. There's information on those edges saying that type of relationship goes. I say, okay, guess what? A directed graph can be modeled as an undirected graph. So let's go ahead and take this edge between B1 and B2. And I can represent that arrow as a topological feature. And so then I see that B1, if it has a self loop, that means it's a vertex in the more abstract directed graph. This little diamond shape. If the diamond shape ends, or on the one on the right, that means the direction is going that way. So in essence, not only can I encode of my graph as topological features, I can also encode my directions of my graph as topological features. So everything is dots and lines. You can think of the universe that we work in as simply things adjacent to one another. Okay. So the second problem. Closing your eyes. And thinking of a flying toaster. Try and manifest in your head, in your mind's eye, a flying toaster. Whatever that looks like to you, whatever those words impinge upon you. The question I have for you is, where does that thing exist? Where does this flying toaster exist? Picture in your head. The flying toaster is from the screensaver. I don't want to say E, so we have physical objects, and we have this little gremlin. This little gremlin represents like a person. We're not talking intrapersonal. It's like a little person. And in between this picture, we have space-time. All of this is a lattice. Some kind of malleable lattice. And if you came to my talk last year, I talked about using graphs to model so we can have a photon bouncing off this particular picture. And this thing is a particle, it's a photon. It's going to go into a superposition. Don't worry about this right now, but there's going to be a wave off of this particular image through space-time. And ultimately manifests itself back as a singular point, as a particle, as a photon. Beholder. And what happens is these photons are little energy packets. And low frequency energy is red, is violet purple. And there's colors in between. Can be easily modeled as a graph. Have particular frequencies, how fast are these traversers coming in? And then in the back of our eye, we have these things called light rods and cones. And there's 3 types. Low frequency energy, medium frequency energy and one that responds to high frequency energy. Think of these like RGB. Your eye is altering like an RGB. So depending upon the frequencies that are coming in, you're gonna get so many various codes in your eye. So that's how we can distinguish color. What you do is you can go up your optic nerve via a bunch of things called action potentials. You have these neurons in your head, depolarize. This is when they get a lot of stimulation on the soma body of the. It's going to send a shoot of energy via depolarization down the axon channel, and it's going to release these things called neurotransmitters into the cleft, which is then going to trigger the next neuron in the line to go ahead and propagate its information. All of this can be as vertices and edges. Neural networks, this has a nice mapping to mapping to graphs. This is something called your lateral genicular nucleus. We start to understand what the velocity of movement. These are things we start to break apart from the image of these photons hitting your eye. It starts to decode information. And this information is just a big tree of feature selections that happens in your brain. And so when it hits your visual cortex in the back of your head and your occipital lobe, you start to do edge detection. So you kind of know that there's this little object right there. And then you start to, in your V2 through V4, you start to realize complex shapes. You start to see more defining characteristics of that particular flying toaster. And then in V5 through V6 starts to merge all that motion information with all that complex shape information, this object moving. And so the way we see it is by looking, when we probe, the brains of monkeys, and we can see that these neurons are reacting to stimulus. We're seeing that it's reacting to edge detection, it's reacting to motion, it's reacting to complex shapes. Ultimately, in your temporal lobe, we're starting to get these things that are called grandmother cells. And people find this to be wildly crazy. In your head, there's a cell in your brain where if I show you a picture of your mother, if I show you a drawing of your mother, it'll fire. If I show you the voice of your mother, it seems that anything that's related to your mother will converge upon these grandmother cells in your temporal lobe. These are kind of like conceptual nodes. The way that the information stimulus came to you, whether it be sound, sight, smell, and the smell of your mother's perfume, it'll fire. Picture of another woman, of a man, and other kinds of perfume, it will not fire. For some reason, with the sense of your mother. And so toaster and flying, for some reason, oddly enough, exist as cells in your temporal cortex. And so then we combine that, and that kind of gives us, we just don't know. That's where the description of cognitive science and neuroscience kind of ends there. And there's this manifestation of your head, the things, the quality that we're experiencing right now, the way everything looks to me, all of a sudden produces this. What is that consciousness that we're existing at? How is that edges? So, is how does the conscious experience, the actual only experience that I know, not the objective that we can quantify with, but how does the conscious experience get encoded? What is the quantum? The quanta of consciousness. Makes no sense. And so in footnote number 4 of the article, we say, okay, processes the conscious experience. As your light cones fire, as you're detecting shapes, that whole chain of events, that flow, that is that yields an epiphenomena of this notion of a toaster. Process a structure. The traversal algorithm can be encoded structurally. So therefore, that whole process that we define, that traversal through the mind, touching all the different various aspects of your neurons and whatnot, that is an algorithm. You can be able to encode it. That's still physically how consciousness has its kind of effect. Everything is a graph when the things that I sense have no kind of discreteness to them, very holistic. Okay. The last one, we're going to talk about how we can alter process. to, like, in computer science, we have this notion of reflection, computer reflection. A program can get reference to itself, or to itself at runtime in order to change. So we have our definition, G, T, psi. We showed in the first section how that can all be represented as a graph. So let's go look at the physical world. The physical world, what do the physicists tell us? Well, there's this structure out there in the physical world, and then there's these transcendental laws of physics that exist. They say how the electrons move, how the protons move, why gravity is the way it is, why space-time, the weight of something. And so these laws of physics seem to be kind of, physicists aren't computer scientists. They don't talk about implementation, prediction. They say, okay, I got a state of something, I got some equation, here's the state. How's it implemented? What do you mean? So physicists kind of never satisfy me. What they do is describe the evolution of something, they can't explain it. And so they say, you have this data structure, matter, energy in this space-time. You have a bunch of energy in space, and then you have something, let's say, quantum gravity. This matter and energy, how it moves, how it warps space-time accordingly. And so, according to our argument, if people want to keep saying, the world's a graph, everything's a graph. Okay, if everything's a graph, how quantum gravity, how all of physics can be folded into vertices and edges. Say everything's a graph. So, let's say we have this structure, right? This space-time, and then we have this quantum gravity. Now, quantum gravity is represented as a traversal. It's an algorithm. The physicists like to talk like this. Okay, there's something on the outside that's interacting. It's rules law upon the world. It's the mediator. This traversal ultimately is a pointer that allows the program to talk to the data. Counter the data counter. Your CPU. Case. If it is the case, the laws of physics are transcendental in this nature, that everything is vertices and edges. And that means that quantum gravity exists somewhere. It has to exist somewhere as vertices and edges. That algorithm exists in the universe. The geometry of, the particles is the quantum gravity algorithm in and of itself. I don't know. The way space-time is shaped is the algorithm. The algorithm exists. It must exist. And you cannot just say, well, it's metaphysically outside the universe. Because if you say it's outside the universe, well, not in terms of vertices and edges. Gravity exists as a structural thing. And that means reversal in space-time graph. That's ultimately what we're doing. I'm going to go ahead and alter the area of space-time. I'm going to create some device. We'll then allow traversals to run through it. If I can get a reference to quantum gravity, traversing the algorithm, the laws of physics. So can I create a traversal such that it gets a reference to the laws of physics, such that I can manipulate the laws of physics? Okay. Because if everything's a graph, then it's vertices and edges. I can drop vertices, I can add edges, I can do anything I want. So how can I manipulate the dots and lines of the laws of physics? So, valuable structure is what we talked about in the first section. All the processing represent all the algorithms as vertices and edges to the laws of physics. How do I get reference to that subgraph of this universal graph? How do I get reference to the definition of warped mass, warped space? Like that. Say, okay, square of the distance gives you how much gravitational effect. Descriptions. That description must exist. How do I get reference to it? And if I can get reference to it, how can I then mutate it? The notion of now getting reference to itself. The laws of physics, the physical world, and the physical world, then again, altering physics in this kind of recursive. That is another problem that I would like to see solved if people want to say that everything is a graph. That it's just dots and lines. So, thank you very much. If you guys follow my work at all, I'm going to be taking I'm going to be writing a book on graph compute. It's going to involve all these kind of concepts. So hopefully in 2020,